So in this example for hypothesis testing on contingency tables for association or independence, we're going to look at what happens if we get expected values that are less than 5. The example we've got here is Miss Vickers, the head teacher of Stoneway Academy. She believes that the length of time staff are working at the school is dependent on their job role. She's collated information for all the staff currently on payroll, and it's given in our table where we have staff working for 0 to 5 years, 5 to 10 years and more than 10 years with the different job roles that they can take in the school. We're asked to carry out a chi-squared test at the 5% significance level to see if Miss Vickers' beliefs are correct. So the first thing I see if I get a question like this is it's specifically asking me to do a chi-squared test, but also it's asking me to look for if two factors are dependent on one another. So that tells me that we are doing our hypothesis test for independence, and I'm going to be using this pro forma here. In the question we are given our two variables, the two things that we are looking to see are associated or not. So the first one is how long they have been working at the school, so I'm going to say let X be the length of time staff have been working at the school. And the other factor is their job role. So I'm going to say let Y be the job role. When we are doing a hypothesis test for independence or for an association, that is always what my null hypothesis is, that the two factors, the two variables, are independent, are not associated. As the question is looking for whether the school is dependent on their job role, the staff's length of working is dependent on their job role, I'm going to use that hypothesis. So my H0 will be that the length of time staff have been working at the school is independent of their job role. They don't affect one another. And therefore the flip side of that, the alternative hypothesis, is that the length of time staff stay working at the school is not independent of their job role. A chi-squared test is always one-tailed, and in this particular question we are being told that to use a 5% significance level. Looking at the contingency table I've been given, I have 3 columns, so I'm going to say that my n is 3. And I've been given 6 rows of data, so I'm going to say that my m is 6. Calculating v, my degrees of freedom, I'm going to do n minus 1 times n minus 1, which is 2 times 5, which is 10. I then need to look at my chi-squared distribution percentage points. I go across the degrees of freedom 10 row, and because it is a 5% significance level, I'm going to go across the 0.95 p-value and read down to find that my critical value is 18.307. I then need to work out my expected values in my contingency table. As always, I need to start with my row and column totals. So I'm just going to add up all the values in each row and then the same for each column. So for senior leadership team, I'm going to do 1, add 4, add 9 to give me 14. For teaching staff, it's 107. Teaching assistants is 28. Pastoral team is 20. Admin staff 26. And other is 34. I'm then going to do the same, work out my totals for the column. So looking at the staff that have worked there between 0 and 5 years, 1, add 26, add 9, add 4, add 4, add 8, and that's going to give me 52. Staff that have been working there 5 to 10 years is 81, and the staff that have been there over 10 years is 96. That's also going to give me a grand total for 229. Once I've got my totals, I can then use the formula to work out the expected values. So the expected value for senior leadership staff that have been there between 0 and 5 years is its row total, which is 14, times by its column total, 52, and then divide that answer by the grand total, 229. So for senior leadership team 0 to 5 years, we would have expected to have 3.179 members of staff. I'm going to work out those expected values for every single combination of lengths of time and job roles to give me my expected values. So the difference we have for this particular question is when I look at the senior leadership team 0 to 5 years, the pastoral care team 0 to 5 years, and the senior leadership team 5 to 10 years, I have 3 values there that are all less than 5. And we should know that if we have an expected value that is less than 5, that means that I can't use the chi-squared to compare my critical values and test statistic. So unfortunately I need to manipulate my data slightly to get those values a little bit higher. To do this, I'm going to combine some of the options in my 2 variables, and I need to do this in the best way that doesn't limit my data too much and that is sensible. So I've got 3 different things that I need to combine here. It would not make sense for me to combine senior leadership team and pastoral care team. They're not 2 things that would necessarily combine well together. I could combine senior leadership team with teaching staff and then combine pastoral care team with admin staff perhaps. However, I think for this particular question, to limit the amount of combinations that I'm doing, the best thing to do will be to combine the 0 to 5 years and the 5 to 10 years columns, making a 0 to 10 and then 10 years plus. So to do this, I am going to take all the values that are in my 0 to 5, and that's my observed and my expected values, and I'm going to add them to all those values in the 5 to 10 years column. So you can see here, if I just go back again, I've got 1 and 4, and then my e-values are 3.179 and 4.952, and I've combined those here to get 5 and 8.131. And I've now made this column 0 to 10 by just combining those blue and red figures. Now all of my e-values are greater than 5, and I can finish off this hypothesis test in the same way that we would any other hypothesis test for independence. I'm going to calculate my test statistic using the formula the sum of O minus E all squared over E. I'm going to use this table to help me just make sure I'm setting it out properly and getting all my values correctly. However, before we do that, we need to just take a quick look at what we've done to the table. We've reduced the number of columns down from 3 to 2, so that's going to affect my N value, which in turn is going to affect my degrees of freedom. I've now got 2 minus 1 times 6 minus 1, which is 1 times 5. So my degrees of freedom have been reduced massively, and this is why it's important we combine the correct rows or columns, because the smaller we make our critical value, or the smaller we make our degrees of freedom, the smaller we make our critical value, and the more likely we are to make errors in our conclusion. So in this particular format, I have reduced my degrees of freedom from 10 to 5, and therefore my critical value, just looking at the table, has gone down from 18.307 to 11.070. Then I'm going to calculate my test statistic. So I'm going to say my observed value here was 5, my e-value here was 8.131. If I work out the difference squared, I get 9.803. And then dividing that by my expected value gives me 1.206. And I'm going to do that for each of those 12 numbers on the table. I'm then going to add them all together. So this final column here, 1.206, 1.670, etc. I'm going to add them together, and that gives me 9.6946, and that is my test statistic. I then, for my comparison, sketch the chi-squared distribution, positively skewed curve, and I add on a cut-off point, a line where my critical value would be, and I mark that as 11.070. I then compare that test statistic with 11.070. So in this case, it goes onto the left. It's still in the belly. So again, we accept H0. And just looking at my critical value, if I'd have reduced those degrees of freedom much more, my critical value would have gone a lot smaller and I would have ended up incorrectly accepting H0. So it's really important we don't reduce it too much. And then in context, I can say there is no significant evidence to suggest that the length of time staff stay working at the school is dependent on their job role. We are saying that Miss Vicker's belief is not